Greetings, students. Today, we delve into an intriguing computational challenge known as the product of array except self, a problem featured on LeetCode as problem 238. The task at hand is to take a given array of integers and construct a new array, where each element at index I represents the product of all the numbers in the original array, excluding the element at index I. For instance, consider the input array 1, 2, 3, 4. The expected output is 24, 12, 8, 6. Here, the element at index 0, which is 1, yields a product of 24, derived from multiplying 2, 3, and 4, while the element at index 1 results in 12, and so forth. What makes this problem particularly captivating is the requirement to achieve this without utilizing division, and to do so in linear time complexity, or ON. As we embark on this exploration, let us unravel the elegant solutions that lie within. A frequency array with a list is a powerful data structure that helps us count how often each element appears in a given list. Imagine you have a list of fruits: apples, bananas, and oranges. A frequency array would allow us to track how many of each fruit we have. For instance, if we have 3 apples, 2 bananas, and 1 orange, the frequency array would show these counts at their respective indices. This structure is particularly efficient because it allows us to count and access frequencies in ON time, meaning it scales well even with large datasets. In contrast, a naive approach might take ON toward time, which can be slow and resource-intensive. To create a frequency array, we simply loop through our list and update the array at the index that corresponds to each element. Initially, we need to determine the possible values in our list to allocate the array correctly. Once it's set up, we can quickly retrieve the frequency of any element, making it a valuable tool for data analysis and manipulation. The function on the slide creates a frequency array from a list of elements. Let's break it down step by step. First, we initialize an empty dictionary called frequency. Think of this dictionary as a counting tool, where each key will represent an element from our list, and the value will represent how many times that element appears. Next, we loop through each element in the list. For each element, we check if it already exists in our dictionary. If it does, we increase its count by 1. If it doesn't, we start its count at 1. This is done using the get method, which helps us avoid errors if the element isn't already in the dictionary. Finally, we create a result list that contains the frequency counts for each element in the original order. This means that for each element, we look it up in our dictionary and grab its count. The function then returns this list, which shows how often each element appears in the original list. This approach is efficient and straightforward, making it easy to understand the distribution of elements in any dataset. The concept of prefix and suffix product arrays is a powerful tool in computing. Imagine you have an array of numbers, and you want to find the product of all elements except for the one at the current index. Instead of dividing, which can be tricky, we use 2 helper arrays, the prefix product array and the suffix product array. The prefix product array at index I contains the product of all elements from the start of the original array up to index I-1. For instance, if our array is 2, 3, 4, the prefix product for index 1 would be just 2 because it's the only number before it. Now, the suffix product array does the opposite. It holds the product of all elements after the current index. So for index 1, it would multiply 4, the number after 3. Once we have both arrays, we can find our desired product for each index by simply multiplying the corresponding values from the prefix and suffix arrays. This method is efficient as we only need to traverse the original array twice, allowing us to respond to multiple queries in constant time. This approach significantly reduces the overall computational effort compared to recalculating products repeatedly. Let's dive into how we can create prefix and suffix product arrays to solve the problem product of array except self. First, we determine the length of the input array, which we'll call n. We initialize 2 arrays, prefix and suffix, both filled with 1s. These will help us compute the products efficiently. Next, we compute the prefix products. Starting from the second element, each position in the prefix array is filled by multiplying the previous prefix value with the corresponding element in the input array. Think of this as building a cumulative product from the left side. After that, we move to suffix products. Starting from the second to last element, each position in the suffix array is filled by multiplying the next suffix value with the corresponding element in the input array. This builds a cumulative product from the right side. Finally, we combine these two arrays. For each index, we multiply the corresponding values from prefix and suffix to get the final result. This approach allows us to find the product of all elements except the current one without using division, making it efficient and straightforward. Optimal space complexity with O1 auxiliary space indicates that an algorithm uses a constant amount of extra memory, irrespective of the input size. Think of it like using a small toolbox for a big job. No matter how many items you're working with, you only need that one toolbox. In this case, auxiliary space is any extra memory we use besides the input data itself. When an algorithm operates in O1 space, it doesn't need additional arrays or structures that grow with the input. Instead, it relies on just a few variables for calculations. This approach is vital in situations with limited memory, like in embedded systems or when handling large datasets. Achieving O1 space often means modifying the original data directly. For example, you might swap elements in an array instead of creating a new one. This not only saves memory, but also speeds up the process by reducing overhead, making these algorithms ideal for real-time applications and competitive programming. The function shown here, double values, takes a list of numbers and returns a new list where each number is doubled. First, we initialize an empty list called result, which will hold our doubled values. This is crucial because we need a place to store the outcomes of our calculations as we go through the input list. Next, we loop through each number in the provided numbers list. For each number, we simply double it by multiplying it by 2. This is a straightforward operation. We then take that doubled value and append it to our result list. Finally, once we've processed all the numbers, we return the result list. Notice how we only used a small amount of extra space, specifically for the result list, which means this function operates with O1 auxiliary space complexity. This is efficient, as we only use memory proportional to our output size, not the input size. To solve the product of array except self problem, we need to create an output array where each element at index I is the product of all numbers in the input array, except for the number at I. First, we initialize an output array filled with wes. This helps us build our results step by step. We also determine the length of our input array, nums. Next, we calculate the left products. We loop through the nums array from left to right. Here, we maintain a variable called left product, starting at 1. For each index, we store the current left product in our output array and then update left product by multiplying it with the current number in nums. After calculating the left products, we move on to the right products. This time, we iterate through the array from right to left. We use another variable, right product, also starting at 1. For each index, we multiply the current value in our output array by right product, then update right product similarly. By the end of these 2 passes, our output array will have the desired products for each index. This method runs in O(n) time and uses O1 additional space, ensuring efficiency even with large arrays. In this problem, we are tasked with generating an output array from a given integer array nums, such that each element output I represents the product of all elements in nums except for nums I. Importantly, we must achieve this without utilizing division, and in linear time complexity, O(n). The constraints specify that n ranges from 2 to 10,000, and each element in nums varies between magnitude 30,000 and 30,000, ensuring that our calculations remain within the bounds of a 32-bit integer. The product accepts self function provides an effective solution for calculating the product of an array of numbers while excluding the number at each index. This method cleverly avoids division, which can simplify many problems but is not allowed here. Let's break down the approach. The function first determines the length of the input list and initializes an output array filled with ones. Think of this output array as a blank canvas where we will paint the results. In the first loop, we calculate the prefix products. As we go through the nums array, we keep track of the cumulative product of all elements before the current index. Each time we move to the next element, we update our running total, prefix product and store it in our output array. Next, we reverse our direction with the second loop to compute the suffix products. Here, we multiply each element of the output array by the cumulative product of all elements after the current index. This means we effectively combine the prefix and suffix products without using division. This two-pass method is efficient, operating in linear time and using constant additional space, aside from the output. The final output array holds the desired products for each index, demonstrating a smart use of both time and space in algorithm design. Let's analyze the complexities of the product of array except self problem. First, we have the time complexity, which is O(n). This means that our solution requires just a single pass through the input array. Imagine you're in a line at a grocery store. If it takes you a certain amount of time to check out each item, the total time depends on how many items you have. Similarly, in this problem, the number of elements directly influences the time it takes to compute the prefix and suffix products. Next, we look at space complexity, which is O(1). This indicates that we're using a constant amount of extra space. Picture a backpack that can only hold a few essential tools. In our case, we modify the output array directly and only need a couple of extra variables to keep track of the products. This efficient use of space means we don't waste resources, allowing us to solve the problem effectively while keeping our memory usage low. Understanding these complexities is crucial for optimizing our solutions in programming challenges.